Hey everyone, and welcome back to the channel. Today, we're diving into the exciting new release of AutoCodeAgent, version 1.8.0. This update introduces some powerful capabilities, particularly around making our Retrieval-Augmented Generation, or RAG, systems much smarter and more adaptive. The headline features are a brand new, versatile reinforcement learning agent, and its application in a system we call RL-Meta-RAG. This new system dynamically chooses the best RAG technique for your specific query. Sounds cool, right? But before we see how it works in practice, let's understand the core concepts behind this new RL agent. So what exactly is reinforcement learning? At its heart, RL is about learning through trial and error, just like humans or animals often do. Imagine an agent. That's our learner. Like the Q-Learning agent in AutoCodeAgent. This agent exists within an environment, the system it interacts with. The agent observes the environment's current state, which is a description of the situation. Based on this state, it takes an action. The environment then gives the agent a reward, positive if the action was good, negative if it was bad, and transitions to a new state. The agent's goal? To learn a policy, a strategy for choosing actions in different states, that maximizes the total reward it collects over time. One popular RL algorithm is Q-Learning, which our agent uses. Q-Learning focuses on learning the value of taking a specific action in a specific state. This is called the Q value, written as Q of S, A. A high Q of S, A means taking action A in states seems like a good long-term bet. A low Q of S, A means this action probably won't lead to good rewards from this state. The agent learns these Q values by repeatedly. First, being in state S. Second, choosing an action A, sometimes randomly to explore, sometimes picking the best known one. Third, observing the reward R and the next state S prime. Fourth, updating its estimate for Q of S, A using the Q-Learning formula. This update considers the immediate reward R and the estimated best future reward it can get from the new state S prime, discounted by a factor gamma, how much we value future rewards. The alpha parameter controls how much new information overrides old estimates. Now, our Q-Learning agent is special because it supports two modes for handling these Q values. First, the simple mode, Tabular Q-Learning. This uses a straightforward dictionary, like a table, to store Q values for every state action pair it encounters. It's easy to understand and guaranteed to find the best policy if the number of states is small and manageable. Think of simple games or grid worlds. The downside? It doesn't scale. If you have too many states, the curse of dimensionality, the table becomes impossibly large, and it can't generalize to states it hasn't seen before. Second, the neural mode, Deep Q Network, DQN. This is where things get powerful. Instead of a table, it uses a neural network, a brain, to approximate the Q values. You feed the network the state, as a vector of numbers, and it outputs the estimated Q values for all possible actions. Its pros: it can handle vastly more complex problems with huge or even continuous state spaces, like sensor readings or complex feature vectors. Crucially, it can generalize. It can make intelligent guesses about states it hasn't seen based on similar states it has seen. Its cons: it's more complex to set up and tune, can sometimes be unstable during training, requiring techniques like experience replay, not in this basic version, and is less interpretable. It's harder to see why it chose an action. It also typically needs more data and computational power. So that's the core idea behind the new RL agent. A flexible learner that can use either a simple table or a powerful neural network to figure out the best actions based on experience. Okay, theory is great, but how does AutoCodeAgent actually use this new RL agent? This brings us to RL-Meta-RAG. Think about different RAG techniques. Standard vector search, like basic LlamaIndex, might be good for simple keyword queries. HyDE, hypothetical document embeddings, might be better for questions needing inferred context. Adaptive RAG might excel at complex queries by first classifying them. Which one should you use? It depends on the query. RL Meta RAG treats this selection as an RL problem. The agent is our Q-Learning agent, specifically in neural mode. The state is a set of features extracted from the user's query, e.g., its complexity, type, keywords, generated using an LLM. The actions are the different RAG techniques available, e.g., Action 0 equals LlamaIndex, Action 1 equals HyDE, Action 2 equals Adaptive RAG. The reward, ideally, comes from how good the results were using the chosen RAG technique. This can even involve human feedback. The goal is for the agent to learn a policy. For this kind of query, state, that RAG technique, action, usually gives the best results, high Q value. It's meta RAG because it operates above the individual RAG techniques, orchestrating them intelligently. As you can see in the video demonstration, I make a request to activate the RL Meta RAG tool. The system initializes the Q-Learning agent in neural mode. Initially, it attempts to select the RAG technique with the highest Q value. However, because we don't have sufficient training data yet, and the prediction error, TD error, is consequently high, we've implemented a fallback mechanism. In this early stage, the choice of RAG technique is actually made by an LLM suggestion. After receiving the response generated by the chosen RAG technique, the user has the option to provide a rating from 1 to 5. This rating serves as the crucial reward signal for training our Deep Q network, DQN. This reward is used to update the network, specifically shaping the Q value for the particular state, the query features, and the selected action, the RAG technique used. By using this 1 to 5 reward, we train the model to learn the expected long-term value, Q value, for that specific state-action pairing. Okay, so let's really dig into this Q-Learning agent and see how it ticks. Basically, it's built on those Q-Learning ideas we talked about. It figures out how good an action is in a particular situation, that's the Q value, by trying things out and seeing what rewards it gets. It uses that standard Q-Learning update formula, tweaking its guesses based on the reward it just got and what it thinks it can get from the next situation. We've got the learning rate, alpha, which decides how much weight to give new experiences, and the discount factor, gamma, which is all about how much it values future rewards compared to immediate ones. Now, the cool thing about this agent is that it can work in 2 different ways. First up is the simple mode. This is your classic old-school tabular Q-Learning. Think of it like the agent keeping a big spreadsheet or a dictionary. For every possible situation or state, and every possible action it can take, it stores a Q value. How does it work? Well, it maps states, which need to be something simple it can use as a key, like grid coordinates, to a list of Q values, one for each action. What's good about it? It's really easy to understand. You can literally look inside and see the value it's learned for taking a specific action in a specific state. Plus, if your problem isn't too complicated and you let it learn long enough, it's guaranteed to find the best way to do things. What's the catch? It hits a wall if there are too many possible states. This is called the curse of dimensionality. The table just gets way too big to handle. Also, it can't really make educated guesses about situations it hasn't seen before. It only knows what it's experienced directly. That brings us to the second way it can work, the neural mode. This uses what's called a Deep Q network, or DQN, and it's designed to handle the problems the simple mode can't. Why do we need this? Because lots of real-world problems have tons of states, or states described by continuous numbers, like sensor readings or complex features. A simple table just won't cut it. So how does this work? Instead of a table, it uses a neural network, kind of like the agent's brain, to estimate the Q values. You give the network the current state, represented as a bunch of numbers, and it spits out the estimated Q values for all the actions you could take. Now, a really important part here is figuring out how to represent the state. You need to turn whatever your state looks like, maybe text, maybe an image, maybe some structured data, into a fixed list of numbers that the neural network can actually process. This might involve scaling numbers, using one-hot encoding for categories, or creating embeddings. The agent actually has a specific part, the underscore preprocess state method, Designed for this, and you usually have to tailor it to your specific problem. What are the advantages? DQNs can handle huge numbers of states, even continuous ones. And the big one, they can generalize. They can make pretty good guesses about situations they haven't seen before, based on how similar they are to situations they have seen. What are the downsides? Well, they're definitely more complicated to set up and get working right. Sometimes the training can be a bit shaky, although this version keeps it fairly basic. It's also harder to look inside and see exactly why it's choosing an action. They're less interpretable. And usually they need more data and more computing power to train compared to the simple mode. So, besides these two modes, the Q-Learning agent has some other essential parts. There's the setup part, Sakudan init, A, where you tell it how to behave. Things like the learning rate, discount factor, how often it should explore randomly, epsilon, whether to use simple or neural mode, how many features are in your state if you're using neural mode, how many actions it can choose from, and where to save its progress. It also needs to save and load what it learns. Save data, load data. For the simple mode, that usually means saving the Q table. For the neural mode, it saves the trained neural network itself, plus other info like how much training it's done. We already mentioned state pre-processing, pre-process state, super important for neural mode to turn raw states into numbers the network understands. Then there's getting the Q values, get Q values. You give it a state, and it tells you the current estimated Q values for all actions. Simple mode just looks it up in the table. Neural mode runs the state through the network to get the predictions. And the core learning happens when you update the Q values, update core value, train step. After the agent tries an action and gets a reward and sees the next state, you call this. Simple mode just plugs the numbers into the Q-Learning formula and updates the table. Neural mode figures out a target value based on the reward and its prediction for the next state, and then it nudges the neural network's weights a little bit, trying to make its original prediction closer to that target. Finally, choosing an action, choose action. This handles the balance between exploring new things and exploiting what the agent already knows. Most of the time, it picks the action that looks best based on the current Q values. But sometimes, with a probability called epsilon, it just picks an action randomly to make sure it doesn't miss out on potentially better options. Usually, this epsilon value gets smaller over time as the agent learns more. Just to make it clearer, think about that simple grid world example again. If you used simple mode, the state might just be the row column coordinates. The agent learns values like the Q value for being at 2, 3, and moving right is. If you used neural mode, you'd first have to turn row, column into numbers, maybe like scaled row number, scaled column number. The neural network takes those numbers in and gives you Q values for moving up, down, left, or right. Training means showing the network lots of these number vectors and the target values they should have produced. So, understanding these pieces, the two modes, why state representation matters for neural networks, and what these key functions do, gives you a really good picture of how this Q-Learning agent operates and how you could use it for different kinds of learning tasks. Alright, so how does this Q-Learning agent actually power our advanced RAG system? Let's talk about the RL Meta RAG implementation. The core idea here is pretty neat. Instead of just picking one RAG technique, like LlamaIndex or HyDE, and sticking with it, we use our Q-Learning agent, specifically in its neural mode with that deep Q network, to dynamically choose the best RAG approach for whatever query the user throws at it. The whole point is to learn the best way to pick a tool over time, so we get the highest quality information back. You can think of it like an intelligent RAG orchestrator. Here's a breakdown of how it actually works when a query comes in. First up, LLM-powered feature extraction. This is where it all begins. When a query arrives, we don't just send it straight to a RAG tool. Instead, we use a large language model, guided by a specific prompt, to really analyze the query. The LLM pulls out key characteristics, things like, is this a factual question or a comparison? What's the topic, like technical or historical? Are there specific names or places mentioned? It even scores things like complexity, ambiguity, and urgency, and notes the query length. All these features get processed, maybe turning categories into numbers, scaling scores, to create a numerical state vector. This vector is what our RL agent actually understands. Next comes the adaptive action selection. Now the system has to decide which RAG technique to use: LlamaIndex, HyDE, or adaptive RAG. These are the actions it can take, and this is where the smarts come in. The system keeps an eye on how well the DQN agent has been doing recently by looking at its average prediction error over the last few times it made a choice. If the agent's doing well, meaning its error is low, the system trusts the policy it's learned. It uses the DQN to estimate how good each RAG technique is for the current query features, and then picks one, usually the best-rated one, but sometimes it explores randomly just to keep learning. But if the agent seems to be struggling, maybe the error is high, or it just hasn't had much training yet, the system plays it safe. It falls back to asking another LLM directly for a suggestion on the best RAG technique for this specific query. This mix and match approach makes the system robust, blending what the agent has learned with the reasoning power of an LLM. After that, it executes the chosen RAG on. Once a RAG technique is picked, the system runs the corresponding retrieval function. Then it either generates the final answer. The information retrieved by the chosen RAG tool is combined with the original query, and another LLM call puts together the final answer that the user will see. Now here's a really cool part: the optional human feedback loop. If this feature is turned on, after generating the answer, the system saves the state vector, the RAG tool it chose, and the original query. Then, using WebSockets, it sends the answer to the front end and asks the user, "Hey, how helpful was this? Rate it 1 to 5. That rating becomes the reward signal. And finally, the learning step. The actual learning for the DQN agent doesn't happen right away. It usually happens later, when that human feedback, the reward, comes back. That reward, along with the saved state and action, is used to train the DQN, helping it make better RAG selections in the future. Throughout this whole process, the system can use WebSockets to send real-time updates to the front end. You can see the features extracted, whether the RL agent or the LLM made the choice, the predicted values, which RAG tool was picked, and if it's asking for feedback. This makes the whole thing much more transparent. So you see, RL Meta, RAG, isn't just some abstract idea. It's a working system using the Q-Learning agent in neural mode right at its core. It cleverly uses an LLM to understand the query, adaptively chooses between its own learned strategy and an LLM fallback, runs the best RAG tool, and even has a way to learn directly from human feedback to get better over time. The advantages here are pretty significant. It's adaptive, handling all sorts of queries by picking the right tool. It's self-improving, especially if users provide feedback. It aims for optimized performance, trying to get better results than any single RAG method could alone. It's transparent, showing you how it's making decisions. And it's a great example of the hybrid intelligence, combining RL's ability to learn patterns with the reasoning power of LLMs. This makes it perfect for building advanced chat or search systems that need to deal with unpredictable questions, learn from users, or manage a whole suite of different information tools intelligently. AutoCodeAgent 1.8.0 really takes a leap forward by bringing in reinforcement learning. That dual-mode Q-Learning agent gives us a solid base for learning from experience, whether we're using simple tables for simpler problems or deep Q networks for complex tasks like this RAG selection. The RL Meta RAG system is a fantastic showcase of this, creating a RAG orchestrator that learns to pick the best tool for the job, adjusts its approach based on how well it's doing, and can even be guided by human input. This really opens up some exciting doors for building smarter, more adaptive, and ultimately more effective AI systems. So what do you think of these new RL features? How might you use the Q-Learning agent or the RL Meta RAG system in your own projects? I'd love to hear your thoughts. Drop them in the comments below. And hey, if you found this video helpful, give it a like, subscribe for more updates on AutoCodeAgent and AI development, and definitely check out the links in the description to dive into the code and documentation yourself. Thanks for watching, and I'll catch you in the next one.